Discussing about the speed of the longitudinal waves, we know that longitudinal waves are mechanical waves which require a material medium for their propagation. Longitudinal waves travel in the form of compressions and rarefactions in which the particles of the material medium vibrate in a direction parallel to the direction of propagation of the wave. Now, when the wave travels in the form of compressions and rarefactions, there is a change in pressure which corresponds to a change in volume. And the quantity which measures the change in volume by that fractional change of pressure is called as bulk modulus. So, the speed of the longitudinal wave in a medium depends upon the bulk modulus and the density. Because of the compressions and rarefactions, the density of the material medium changes. That is, when there is compression, particles of that material medium come closer, so density increases. In a rarefaction, the particles go away from each other, that is, the density decreases. So the speed of the longitudinal wave depends upon two factors. One is bulk modulus and another is density. And the relation between the three, that is velocity, bulk modulus and the density, is got from the dimensional correctness of equations, as already done in case of transverse waves. Now the bulk modulus B is equal to change in pressure delta P divided by fractional change in volume, that is delta V by V. So it is evident that the bulk modulus should have the dimensions of the pressure, because it is the ratio of volume and volume. So this denominator is dimensionless. So here we are left with the numerator. That means the bulk modulus should have the dimensions of the pressure. Now, as already told, the speed of the longitudinal wave depends upon the bulk modulus. Let this be written as bulk modulus to the power A, but we don't know the exact relationship, but it depends upon B. So for dimensional correctness of equations, we let it as V directly proportional BA and V directly proportional rho B. Now, so V is equal to K B times A and rho times B, where K is a constant. From the observations, the value of K has to be found as 1. So velocity depends upon bulk modulus and the density. Now, going to the dimensional correctness of equations, we know that the dimensions of velocity. So if V is equal to B times A and rho times B, from this equation or from the dimensional correctness of equations, we will see what is the power of A and what is the power of B. That is the dimensional correctness of equations, and we know that the dimensions of velocity are m0 Lt minus 1, as already stated that bulk modulus has the same dimensions as that of pressure, that is force per unit area. So its dimensions are ml minus 1 T minus 2, that is force per unit area, and density is mass per unit volume, and that means it is ml minus 3 raised power B. Here we have got similar terms m and m, bases are same, powers are added. Let us solve. So we get m0 Lt minus 1 is equal to m times A plus B L times minus A minus 3B and T times minus A, T to the power minus 2A. Now comparing the powers in the equation, we have A plus B is equal to 0, minus A minus 3B is equal to 1, and minus 2A is equal to minus 1. Now from the last one, we have minus and minus cancels out. A is equal to 1 by 2. Now in the first, A plus B is equal to 0. So 1 by 2 plus B is equal to 0. So B equals minus 1 by 2. Now we have got the powers. So V equals to bulk modulus to the power 1 by 2 and rho to the power minus 1 by 2. Solving it, V is equal to root of B divided by rho, where B is the bulk modulus and rho is the density. So the velocity of a longitudinal wave in a medium is equal to the square root of ratio of bulk modulus and density of that medium. If a solid bar is hit by a blow at one end, the relevant modulus of elasticity here to be taken is Young's modulus of elasticity in place of bulk modulus. So the velocity of sound equals to root of y, that is Young's modulus of elasticity, divided by rho. In case of longitudinal waves in a medium, the velocity is equal to root of bulk modulus of elasticity divided by rho. Thank you.